We'll be discussing a bit about recommendation systems using RNNs and two-tower architecture. So what is the goal? The goal is to create a Google-like search. So whenever you go to Google and search something like what is pi, the Google goes into list of all the documents that's available and finds you the top 10 relevant documents. So have you ever wondered how Google did that? So there is something called embeddings. We do all know that machines don't understand the language as we do. Everything should be converted into the numbers. So that's basically embedding. We want to create a numerical representation of any given data. So let's say we have a query, what is pi? The pi is converted into something like this. First tokens, and then IDs, and then embeddings. So embeddings are just a unique representation of a particular token. In our case, it's a word. So embeddings are a numerical representation, or in other words, a vector representation of a given word in a multidimensional space. So here I have chosen 5 dimensions. 5 dimensions. But you can pretty much choose any dimensions you want. So the standard is something like 300 to 500 dimensions. So for the ease of conversation, I took a smaller one. So basically, we tokenize, we create IDs, we embed for all the queries and all the documents or all the web pages that's available in the internet. So what happens after that? We created tokens and IDs and embedding for any query and all the list of websites that's available in the internet. So what we're going to do after that? So basically, we're going to use machine learning and deep neural networks like RNNs and two-tower architecture to build a relationship between a given query, which is in a numerical form, and the list of all the relevant documents. So we will see that in detail. Any given query is parsed into your neural network, something like this. So an RNN, it could be an LSTM, it could be a GRU or bidirectional RNN or transformers in the most cases. So a query is sent into a neural network with its random weights and biases. Then it gives you an encoding. And we send in all the relevant documents and the non-relevant documents into another architecture, the second tower, and it forms a relevant encoding and a non-relevant encoding, something like this. So why do we have a relevant and a non-relevant document? So basically, we are telling the machine for any given query, this is the relevant document and this is the non-relevant document. So that way, the machine can understand, the neural network can understand what is the right answer for a given query and what is not the right answer for the given query. So once the query and the documents are sent into a two towers, we get the encodings. So once we have the encodings, we find a cosine similarity between a given query and a relevant document. And we also find a cosine similarity between a query and a non-relevant document. And we send it to a triplet loss, and it gives us one single value. Based on that one single value, we backpropagate and calculate all the new weights and biases. So based on number of echoes, it goes backwards and tries to reduce the loss by updating the weights. We use the chain rule and the differentiation to do that. So all the squiggly lines that you see here will be updated at the end of the process. And once it's updated, we take all the documents, in our case, all the websites in the Google, and we send it to a neural network with the updated weights and biases, and then it gives us the new encodings for each document in the Google. So whenever you go to Google and search something like how is the weather today, basically it goes to a neural structure and it is converted into encodings, and we already have the encodings for all the documents in the Google. We try to compare the similarities between those encodings. So we take a numerical representation of a given data, and we take a tried numerical representation of all the documents and try to find a similarity using cosine similarity and sort out the answers. So that's how, for any given query, the Google is able to list the relevant documents that's available in the internet. So what is the conclusion? So this is a simple model. In reality, it's much more complex. We have n number of data and we have data in different formats. So this is just an outline of how to recommend something in the internet. So it could be pretty much applied in so many situations, maybe your Tinder, maybe your Netflix recommendations. So it could be pretty much applied in all the situations. So we need to convert the information into a vector representation and find the relationship between your personal tastes and all your relevant searches in the past. So I did few experimentations we did. So I have used a subword tokenization, but we could use a whole word tokenization or a sentence tokenization. We could use different embedding styles. So I have used word to vec, and we could also use padding and masking to reduce the computational cost and increase the efficiency. And we could use different RNN structures. I have tried with LSTM, GRUs, a basic RNN, and a bidirectional RNNs. And designing the architecture, I have a simple architecture with 32 hidden neurons, but we could try with more layers and more hidden neurons. And we could obviously play with the learning rate, epos, and the momentum. And I have used stochastic gradient descent as an optimizer. Again, there are a few other options. So I used a loss function that's a triplet loss. Obviously, we can use an Euclidean loss. And yeah, there are a few other things. And we could increase the size of the data for better performance. So this is just an outlook of how a recommendation system works. So I have even created a code version of it. So basically, I have imported a data set that looks something like this. I can show you. Here. Just surprising. All the arrays must be of the same length. Okay, not really sure why this error occurs because I just ran this program. But yeah, you can see the data. It's something like this. So we have a query and a relevant document and some URL for the relevant document. Basically, I have created a query, a relevant document, and a non-relevant document for it. And then I have used embeddings from word to vec. Yeah, you can see here I have used word to vec embeddings. And I got something like 9,000 embeddings. So I have sent in my data and I have created tokens. I couldn't find embeddings for 834 words. And for 104,000 words, I was able to find the embeddings. And basically for the ones that I couldn't find embeddings, I have used zeros as an embedding. And the embeddings look something like this. I have created a vector shape, vector size of 50. And it is basically converted into tensors. And I have padded it on the maximum length. So, and then I have batched it. Then I have tried with RNNs, GRUs, and LSTM. So this one is on the GRU part. And I've trained the model with some parameters. And yeah, I've cached the documents with the trained weights. And basically, I send in a query, something like this. And it is also pre-processed. And then it is used for prediction. So the top 5 predictions based on a given input. So I'm pretty sure that the results are not really good because I've took a data set of just 100. So in real case scenario, the data set has something like, if you see here, 82,000 queries and such relevant documents. But for sake of simplicity and ease of programming, I took really a small data. So if I could increase the complexity of the model and the data size and tune the parameters, I'm pretty sure that I could get in some better results. And I try to deploy it in the streamlit using streamlit and the fast API. So I was not able to open it at the moment. So this is basically a screenshot of it. And yep, that was it about all this week. Thank you.